So I'll start directly. So what are we about to do? So the goal for this part of the lecture is to classify semi-simple algebras. And what we did so far by Serre's theorem is that we reduced this classification problem to a different classification problem, namely to classify root systems. Right, so these root systems were some geometric notion, point configurations in a Euclidean vector space that fulfill a certain number of axioms. And we know once we classify those, we obtain the classification of semi-simple algebras. So, so this is our step 2, if you want, in our classification of semi-simple algebras. Do precisely this: classify root systems. So how do we do this? Right, so say, now I have to reintroduce the notation. So we had E be a Euclidean vector space, and phi a root system. So just think of our famous hexagon or the other examples I showed last time. Aha. P should be the weight lattice, so I'm not sure whether I defined the weight lattice in the abstract setting. So remember, the whole story was as follows. Once we have a semi-simple algebra, then we know what the weight lattice is, right? This is just a set of weights which occur as weights of an irreducible representation. And okay, then there's this weight lattice, and in the abstract setting, well, there are no representations a priori. There are no weights. There is just this Euclidean vector space and this root system. So we can just define the weight lattice in the abstract setting. So this is the set of all elements of this Euclidean space, such that lambda alpha check is an integer for all roots alpha. So this was by definition just 2 times the inner product lambda alpha divided by norm square of alpha. Anyway, so it turns out that I guess we showed this, that for our concrete root systems which come from a semi-simple Lie algebra, we can describe the weight lattice by this property. So we just use this property to define the weight lattice also in the abstract setting. So now we're considering an abstract root system, and we just, in this case, as there are no representations, we just define the weight lattice by the same property. So what's the trick we are going to employ now? We consider a subset delta of our root system such that delta is a basis of E. So let's draw our favorite A2 type root system. So these 6 points form the form the root system phi. So we could take any two linear independent. For example, these would form a potential set delta, or these two. Just any subset which is a basis of the vector space. Then there's one thing which is already clear, namely, by our axioms, for all roots, this property holds. This was one, I don't remember which one, I guess the fourth axiom for our root system. When I put a root and I compute this expression, bracket, root, other root check, then I always get an integer. So in other words, my root system is contained in the weight lattice. So I pick a basis, delta, which is contained in the root system. So the basis is consists of vectors in the lattice. So whenever I express another root in terms of this basis, that will have rational coefficients. Right, so there can't be any square root of 2 or any strange numbers, just because our basis is consists of vectors in the lattice, and our roots, or things we want to express in the basis, also are elements of the same lattice, so the coefficients must be rational numbers. And it turns out that one can choose delta in a clever way, and then one gets even more. So that's the following proposition. So it's possible to find such a basis delta of E such that the following property holds. I pick any root and I consider the coefficients of my root with respect to delta. So they are all integers. So there are two properties which are supposed to hold. First property, that all coefficients are integers, and the second property is that depending on alpha, they are either all positive or all negative. Well, that wouldn't work with any set delta, which is a basis, but let's just consider this second one. So say this is alpha 1, this is alpha 2, and for delta I take alpha 1, alpha 2. So what are the coefficients? For alpha 1, of course, it's one of the basis vectors, so this is 1, 0. Alpha 2, similarly, it's one of the basis vectors, so this is 0, 1. So what are the coefficients for this root? This is just alpha 1 plus alpha 2, so 1, 1. So let's have a look at this root. How do I get here? That's just minus alpha 1, so this is minus 1, 0. This root is just minus alpha 2, so the coefficient vector is 0, minus 1. And this root is minus this one, so the coefficient vector is minus 1, minus 1. Well, in this example, one can just see it by checking it. Each of these vectors has integral coefficients, and either they are all non-negative, namely here, here, and here, they are all non-negative, and for the other three ones, they are all non-positive. So this is proposition and definition also. Such a delta is called a base of the root system. So it's a particularly nice basis which has this extra property. Yeah, let me comment on the proof. Of course, also only a sketch of proof. So the idea is somehow there will be positive and negative roots after I found delta. Namely, the positive ones are those where the coefficients are positive, and the negative ones where the coefficients are negative. So here, these would be the positive roots, these would be the negative roots. So in order to find such a set delta, let's just first try to decompose our set of roots into positive and negative roots. So we would choose a hyperplane, linear hyperplane. Say H in E. Such that H contains no roots. Now here, for example, I could take this hyperplane. So there are no roots on the hyperplane. They're either on the one side or on the other side. So I'll just choose that, and I choose a positive. Choose one of the of the half spaces. So here I could just fix this half space and say, okay, I want this half space to be the half space containing the positive roots then. So how do I find my roots delta? So first I say phi plus, this is or my set of positive roots. I just define this as being the set of roots which are contained in the, so H plus is the positive half space I've chosen, so phi plus should be the set of roots contained in this positive half space. So these would be these three roots here in our example. And delta, the set of all roots alpha in phi plus, such that I cannot decompose alpha as a sum of two other positive roots, right? So unfortunately, this example is a bit too small to be really convincing, but anyway, let's stick to it now. So I have to exclude somehow this root. This should not be part of my basis. Well, how do I recognize this? Well, this is decomposable. I can write this one as a sum of this one and that one. And of course, whenever I have a basis element, this is not possible. So somehow this is the construction, and then one has to show that the construction actually works, so that when I construct my set delta in this way, that it will have this property. Anyway, so so it turns out that each root system has a basis. It has a base, sorry. These words are a bit confusing. Of course, each root system has a basis, but even each root system has a base. So why would we consider such bases or bases? And the reason is that they allow for numerical invariance. So using these bases, I can associate a bunch of numerical invariance to a given root system. And of course, then the claim is at some point I have enough invariance so that they characterize my root system, and then I have a classification. So how does this work? With the following definition. So I fix a root system phi, and set alpha 1 through alpha n a base from a root system. Then I consider the following matrix C. So this is a n by n matrix, and the general component is, well, this is not so clear. Alpha I, say it's this one, alpha I, alpha j bar, alpha j check. So just as a remark, this really depends on the text you're reading. Some have the transpose. So I just picked one of the two conventions now. This matrix is called the Cartesian matrix. Of phi. Yeah, example, one of the examples I put on the exercise sheet, so you compute the Cartesian matrix of the root system of type B2 for Thursday, but for now let's consider phi of type A2. So this is our famous hexagon. Right, I think I already did the relevant computations, so let's just recall it. So first we have to fix the base. Let's just pick the same one. So this was alpha 1, alpha 2. So we checked that this is a base. So what's alpha 1 check? Well, that's easy. So the general thing, well, let's just write down the formula. This is 2 alpha 1 divided by alpha 1, so this cancels and we just obtain 2. So let me write down the Cartesian matrix here. So the 1, 1 component will be 2. What about alpha 2? Well, this will also be 2, of course, by the same reasoning. So we already have our first proposition, if you want, that the diagonal matrix of a Cartesian diagonal components of a Cartesian matrix are always 2. So what about the mixed ones? Yeah. So I think last time I already showed the niveau hyperplanes for this root system. So now we have alpha 2. So the kernel of alpha 2 is, or the orthogonal space of alpha 2 is this one. So this is the niveau 0 hyperplane for this expression as a function of alpha 1. The picture is unfortunately not so good. So this is the niveau 1 hyperplane. Here's the niveau 2 hyperplane. So again, we have our verification that alpha 2, oh, I forgot the check here. Alpha 2 check is 2. And this just corresponds to the fact that here my alpha 2 itself lies on the 2 niveau hyperplane with respect to alpha 2. But the one I'm really interested in is this one. So alpha 1 lies on the -1 niveau hyperplane, so this is -1. Or I don't know, I always like looking at these pictures, but you can also just you can also, if you don't like this picture drawing, you can just compute it. Take the definitions of the root system and compute it, and then see this. and the other one, alpha 2, alpha 1 check, will also be -1 here. So this is symmetric. But again, this is a special case for type A. For example, in type B, we'll see that the Cartesian matrix is not symmetric, so there is a choice here whether this matrix is called the Cartesian matrix or its transpose, and depends on the author.
How did you read off those numbers from the level set?
I think it's level set. Right. So there are two level sets I draw. I can draw here in green. These were the level sets for the function alpha 2 check. So I consider this expression here as and then, right. This is a linear functional because, yeah. All right, good.
So the symmetry is really by accident.
Right. So we'll discuss on Thursday this example, this other root system of type B2, which is this point configuration, and there it won't be symmetric. So. Okay. This is how we defined the Cartesian matrix. And it's somewhat useful to represent these Cartesian matrices in a graphical notation, just to have an easier overview. And these are the so-called Dünken diagrams. Somehow I'm losing. No. First the theorem. So as I said, I want to consider these Cartesian matrices to have numerical invariance, which help me in the classification of root system. And of course, for this to make sense, I need the fact that these are actually invariants. So this is the following theorem. So if I have a Cartesian matrix, well, one thing I can always do is I can renumber the basis vectors. Right? So my base was just a subset, so there is no intrinsic ordering here. When I write them down, I have to pick some ordering alpha 1 through alpha n. How would the Cartesian matrix change if I change my ordering here? Well, this would correspond to a relabeling of the rows and columns here. So this is a permutation of this matrix. I would somehow have to permute the columns, and then I would have to permute the rows in the same way. So then I obtain the matrix which corresponds to the same, which is the same matrix just with respect to another ordering of my elements of the bases. So of course I cannot get rid of this, but if I consider my Cartesian matrix just up to reordering, the base, then this depends only on phi, the root system. So not on the choice of my base. Say it again in other words. So how do I construct such a Cartesian matrix? Well, I have given a root system, and I want to associate this Cartesian matrix to the root system. But in order to define it, I have to choose a base, so there's the first choice. Then I have to choose an ordering of the base. This is my second choice. And then I can write down this formula and get my Cartesian matrix. So you can ask, what happens if I would have altered any of these choices? Well, say if I would have taken the same twice, if I wouldn't have altered the first choice, so I take the same base, but I would just have altered the second choice, so I would have altered the ordering, then of course the Cartesian matrix will change, but in a very easy and predictable way, just by permutation of the rows and columns. So on the other hand, what happens if I already changed the first choice? For example, here in my root system, we chose this base here is delta, but already by symmetry it's clear that this set is also a base, so we could have taken this as delta, or maybe this one. So how would this have affected the Cartesian matrix? And the answer is not at all. So if I had chosen delta double twiddle, another base, then with the correct ordering of the elements of the bases, I would have obtained the same Cartesian matrix as the one we computed here. Or if I had chosen the other ordering, then I would have obtained, well, in this case, also the same Cartesian matrix, but in general, a Cartesian matrix obtained by permuting the rows and columns. Yeah?
We could restate that a couple of ways, I guess. So that given any base, there exists an ordering which will give the same card.
Right. Yeah, this is maybe a more formula.
Or we can look at all of the possible orderings, that set of n factorial orderings, and they're the same no matter what.
Right, right. Yeah. Yeah.
Well, that's not obvious.
No, it's not. But that's
so it's sort of an invariant.
Excuse me?
So the Cartesian matrix is sort of an
right, yeah, it's an invariant.
of the root system.
Exactly. Yeah. Up to this small, well, there are, if you really want to formalize it, I think the easiest way is to use your second choice and say, well, the invariant is the set of all Cartesian matrices, or, yeah. N factorial. Yeah, so this is this. This will help with the classification, right? So I think I didn't want to comment on the proof. Yes, I did. So also a sketch of proof. I consider the following subgroup of the group of isometries of E. E is an Euclidean vector space, so it's clear for a linear map what it means to be an isometry, just that one that preserves the inner product. And now I'm considering the following subgroup of the group of invariants. It's the group generated. So this notation now means the group generated by the reflections as alpha, where alpha is an element of the root system. Remember, as alpha was the reflection at a orthogonal. So this is certainly an isometry because it's just a reflection. And the composition of isometries is also an isometry, so I can take the group generated by those, and it will be some subgroup. Well, so far, so good. This is the so-called Weyl group. And one of our axioms was that this is just a side remark. So one of our axioms was that phi is as alpha invariant for all alpha. Right, so this was this symmetry property. So it's also invariant under compositions of these as alpha. So phi is actually W invariant. So meaning if I take any isometry contained in this group W, and then it will send roots to roots. And so how does one prove this? By the following statement. Whenever I have bases, say delta 1, delta 2 of my root system, then I can find an isometry W contained in this Weyl group such that W of delta 1 equals delta 2. So this isometry sends delta 1 to delta 2. And, well, then because it's an isometry, it's clear that it preserves the inner product. So it preserves this angle check expression. So it preserves the Cartesian matrix. So this is the proof here. Maybe let me also just indicate, for example, if this was here delta 1, and then this is delta 2. Well, how would I transform delta 1 into delta 2? In this case, I just need one reflection. Namely, I'll say this is my root alpha I chose. Then this is the hyperplane alpha perpendicular. So S alpha is the reflection at this hyperplane. So this will just send delta 1 to delta 2 and vice versa. And, well, to transform this set to this set, that's a bit more complicated because, well, there is a reflection, but we cannot use this reflection along this line because there is no root here, right? So you really need to consider the group generated by the reflections. Are you interested in that?
So you do it as a composition.
Right, yeah. I have to compose two reflections and then I can send this one to this one. Right. So this is the sketch of proof for this theorem. So now so now we know that Cartesian matrices are important because they are actually invariants, and now there is this useful graphical representation. Of Cartesian matrices. So the first observation is that one can show that all Cartesian matrices will have the following properties. Say, let Cij be a Cartesian matrix. Then Cii equals to 2 for all I. Well, this is obvious. Well, we already noticed that when we did this example. Then there are other properties which are less obvious. So these are propositions or lemmas to show. Namely, Cij is non-positive whenever I is not equal to j. So all off-diagonal components cannot be positive. So here in our example, that just to check briefly, this was actually the case. They were indeed both negative. And the third property, if I is not equal to j, so I look at off-diagonal components, then Cij is negative if and only if Cji is negative. So this excludes, say, the following. By this rule, we know that the following matrix cannot occur as a Cartesian matrix. So the first rule is fine. On the diagonal, we have 2's. Second rule is also fine. On the off-diagonal, we don't have any positive numbers. But the third rule is violated here because here we got 0. So we're supposed to have 0 here also. But here we have a negative component. So this is excluded by the third rule. Also, these are small lemmas one can show. And then the idea is to represent C, a given Cartesian matrix, as the adjacency matrix of a directed graph. Omitting edges which are already implied by these general properties every Cartesian matrix has. Right? So I make this more precise just with examples. Let's consider the Cartesian matrix we just calculated here, 2 minus 1. So which graph would we associate? It's a 2 by 2 matrix, so we need 2 vertices corresponding to the rows and columns. Well, then there are these diagonal components too. We don't have to denote them in our graph at all because they're always 2. We know from our first rule they will be 2. So in order to reconstruct our Cartesian matrix from the graph, we don't need to put anything here. And then we have a -1 here at the 1, 2 component, and also a -1 at the 2, 1 component. So I would just indicate an unoriented edge here. Say our Cartesian matrix would look like this. So, well, what's the graph? Again, it's a 2 by 2 matrix. So I need 2 vertices. These are right. Thanks. Thanks. -1. Exactly. So here I have a -2 component in the 2, 1 entry. So we'll draw 2 edges from 2 to 1. Then I have a -1 component here in the 1, 2. So I would have to remember this by 1 arrow in the other direction, from 1 to 2. But this is already implied by the third rule. Whenever I have a -2 here, I must have something negative here. So some of the default thing to have is -1, so I omit this arrow.
Why can't it be -2?
It can, but somehow this is the default case. So if it's
Okay, so, the default case.
the default case is if I
So you don't indicate the default case.
yeah.
All right.
So how do I somehow this is it's always hard to write these rules explicitly down. Let me just indicate some more examples. So, for example, if the matrix would look like this, I just put some more examples, and if there are any questions after the examples, then. So this would give this Dynkin diagram. Then what else? Maybe we do a 3 by 3 thing. There could be zeros here and there, and then a -3, -1. So what would be the diagram here? That would be 1, 2, 1, like this. Or
everything else is default.
yeah.
Right.
So right. Default thing is first all off diagonal elements are 0. Then whenever I put arrows, directed arrows, then say I put 3 directed arrows, this gives a -3. And then wherever I cannot put 0 because of this rule, there I put -1. Maybe let me.
So the -1 is by default.
Right.
The 2s are by default. What about the 0s?
These are also by default.
3, 1, and 3, 2 entries.
There is no arrow between
Okay. Yeah.
2 and 3. So
Okay.
and there is
So
no.
when you don't have an arrow, it's by default. Okay.
Right. Yeah, maybe I just write down the algorithm to how to reconstruct C, the matrix, from the graph. So I start with the following matrix, all diagonal components 2, all other components 0. Then for all edges say I, J, decrease C, I, J by 1. So here I had to decrease C to 1 by 3, because there are 3 edges directed to the one direction. And as the last step, and unoriented edges count as, so this counts as having an edge in each of the direction. For example, here I would just indicate 2 unoriented edges. That means -2 everywhere. And the last step is replace forbidden zeros by -1. Because of this third rule, some zeros will be forbidden, because I have say here, if I follow this algorithm, then at some point I'll have this matrix.
So how do you decrease Cij by 1 in your example?
Let me just.
You say.
So let's just do that.
4 edges I and J.
Right.
Yeah. So you put zeros everywhere.
So I put zeros everywhere. Then I look at the edges.
Yeah.
So there are 3 edges here.
Oh, okay, all right.
So
Okay.
I consider. Yeah. No, yeah. So now here I put it in this iterative way. First I consider the top edge, then I have -1, then I consider the medium edge, that gives me -2, and then I consider the last edge, that gives me -3. Or I don't know. I haven't found the optimal way to write this algorithm down. What could I?
Replace forbidden 0 as -1. Okay.
Right. So this would be this 0 over here. It's forbidden because it's. Yeah.
Is there a way, so a graph where we replace that -1 with a -2, does that correspond with 2 edges from 1 to 2 in the opposite direction then?
Right. So, yeah. So I didn't put this in the examples because, as we will see now in the classification, this doesn't occur. So one never sees these images, this case in practice. But yeah, as you say, this is in theory how one would do this. So say 2, 2, -3, -2. I would denote this by so this would be the -3, -2, and then there are no forbidden zeros left, so don't have to do anything this step. Yeah, so I'm not sure whether I mentioned the name. So these are these Duncan diagrams. Well, it's associated with C, but C itself was associated with a root system. So let's also say the directed graph is associated with a root system. And this is called the Duncan diagram. So in fact, this is just a notational convenience. There is no more or less information in the Duncan diagram than in the Cartesian matrix. It's just because people tend to think graphically and to like graphs. So it's a convenient way to write down Cartesian matrices by this Duncan diagram. But
That's very interesting. You can use this then to write down the Cartesian matrix of E8.
yeah. Yeah.
It is hard to remember.
Right. Yeah, in fact, that's what we'll do. But let me just give one lemma before I write down the Cartesian matrix of E8. Lemma and definition. So say we have a root system phi 1 contained in some Euclidean vector space E1. Say we also have a root system phi 2 contained in some Euclidean vector space E2. So root systems both. Then I can construct a root system in the Cartesian product. So I consider that just the product vector space with a, there is a natural inner product here. So it becomes a Euclidean space. And I consider the following root system. First, phi 1 cross 0 union 0 cross phi 2. Wrong parentheses, like this, right? So this is a root system in the Cartesian product. So I consider all elements here are tuples, of course, and I consider tuples where the first component is a root and the second component is 0, and I consider tuples where the first component is 0 and the second is a root in the other vector space. And if I put them together, then I claim that I get a root system in the Cartesian product. So this is easy. Just maybe it's not a lemma, but an observation. And so important root systems, or the basic root systems, are those which cannot be decomposed this way. And these are such irreducible, right? So this is the definition, are called irreducible. So what I do to classify all root systems is I just classify the irreducible root systems, and then I say, well, I will obtain all root systems by iterated application of this construction here. Yeah. And this is done by the following theorem. How did I put it? So let phi be such an irreducible root system. Then the Duncan diagram of this root system is one of the following. The first possibility is that I have just a linear graph say with n nodes or vertices. So this is what's called of type AN. So here we recognize our SL3. Put it. Now recall we calculated the Cartesian matrix to be this one, so the Duncan diagram is this one, so this is of type A2. So here we find our SL3, the root system of SL3, it's one of those. Then next property, next possibility is also we have a string as before, and then double edge, and here with n larger or equal to 2 vertices, right? Because if I have one vertex, then somehow this double edge doesn't make sense. So this is what's called of type Bn. Then there is a possibility to also have a long string and then a double edge facing to the center. And here the convention is to consider this with n bigger or equal to 3 vertices. So this would make sense with 2 vertices, of course, but then it would coincide with this case. So if we want a nice classification where every case only occurs once, then we have to disallow n equals to 2 for one of these 2 cases, and the convention is to omit it here. So this is what's called of type Cn. And next possibility, also get a long string, and then this branches like this. So this only makes sense with n at least 4 vertices. Right, so that's the crucial configuration is here, this star configuration with a center vertex and 3 arms, and then one of the arms is prolonged. So I need at least 4 vertices. So this is type Dn. So these are the so-called infinite series, because there is a parameter here, discrete parameter n, and then there are finitely many more. This is of type E6. So the index always gives the number of vertices. I think, yeah, I explained before, the index is the dimension of the Cartan subalgebra. So it's the dimension of the dual, and as the vertices correspond to basis vectors of the dual, it's clear that the index always gives the number of vertices here. So this is E6. Then there is E7. And E8. So just it's again always for the E types, it's the central configuration, one central vertex, then one arm of size 2, one arm of size 1, and then one arm of variable size, which becomes longer from E6. It's always of size 2. E7 is of size 3. E8 it's of size 4. Then F, of course, 4. And G2. And that's it. Just check that. EFG. Yeah, so I won't say too much about the proof. This is elementary, but tricky and long. So by elementary, I mean you don't need any fancy theory. I don't know. Consider the homology of the dual of whatever of the configuration, and use some fancy theorem. But it's just well, you play with show some properties which these Cartan matrices have, and then you successively exclude certain configurations which can occur, and somehow then it's just these which remain, and then you explicitly construct root systems which have these Dynkin diagrams, so you show that these are actually do occur. So it's, I don't know, to me it's not very insightful, the proof, but it's just, well, just have to do it. Well,
It's very nice. It's very, very nice.
So these are all the possible
Very good.
Simple. Yeah, let me, so if you notice there is a gap between 517 and 519. Somehow I was so, I wanted to show this nice theorem, so I skipped the remark 518, which I will do now. So how does this relate to the Lie algebras? This construction so recall we wanted to classify semi-simple Lie algebras, and these are classified by all Dynkin diagrams of all root systems. But here we do not consider Duncan diagrams for all root systems, but just for irreducible root systems. So, and the other root systems are obtained from the irreducible ones by this construction. So, to what construction on the Lie algebra level does this correspond? So if G1, G2 are Lie algebras, with root systems, say phi 1, so this is contained in H1 R dual, and phi 2, this is contained in H star R2. Well, these are the root systems of these Lie algebras. Then I can consider the direct product Lie algebra. So this is a vector space, just the Cartesian product of the two, and the bracket is defined naturally. So if I, anyway, so there's a canonical way to define the bracket here, and it's also easy. So this thing has the root system, well, exactly given by this construction. So it's phi 1 cross 0 union 0 cross phi 2, right? So somehow what we haven't accounted for in this classification are semi-simple Lie algebras, which can be decomposed as a direct sum of other semi-simple Lie algebras. So, and this also finally explains this strange notion of being semi-simple. Where's the semi here? Lie algebra, which is a semi-simple, and does not decompose this way, is a simple Lie algebra. Somehow I'm telling the stories now backwards, or in the other direction than most of the books do it. So if you look in the books, you'll see another definition of simple Lie algebras, which is equivalent. So, but somehow, so there is these simple Lie algebras, and then there are the semi-simple ones. These are the ones which I get by this Cartesian product construction from the simple ones. And so this is the answer to your question, right? So in this classification classifies the simple Lie algebras, not the semi-simple ones. Oh, so maybe I should also write this down as a corollary or something.
So the simple Lie algebras are the ones that are classified by the irreducible magnetic diagrams.
Yeah, exactly. Well, and the other, to classify the other ones, this is also easy. It's so we have to think about how does this construction here, how will it be reflected in the Duncan diagram, and this will be just the disjoint union of Duncan diagrams. So if you have an arbitrary semi-simple Lie algebra, then its Duncan diagram will decompose into several connected components, and each connected component will be one of those. So, right, to classic, yeah, exactly. So actually, right, so arbitrary semi-simple algebras are classified by formal combinations of these Dynkin diagrams, where each Dynkin diagram can occur with an arbitrary multiplicity. Yeah, I think I'm already over time. I'm wondering why Arek doesn't stop me. Anyway, let's stop here. So, yeah, for Thursday there are. I made a smaller exercise sheet because I wanted you to have more time also to start revising if you want. So you're invited to. You won't be there anyway. Those who are there are invited to prepare questions also, because I don't think we'll need the entire lesson to go through these two exercises. So anyway, if there is anything left over from the semester.